Welcome back to Advent of Code 2021, day 8. Okay. Welcome in, Amaro. Yeah, I got 7 done yesterday. They weren't too difficult, like 20 minutes each or something. Alright, day 8. Day 8, 7-segment search. You barely reach the safety of the cave when the whale... Oh yeah, we're being chased by a whale. Whale smashes into the cave mouth, collapsing it. Sensors indicate another exit to this cave at a much greater depth. Basically, this whole 2021 is themed around basically Subnautica. We're in a submarine exploring places. What you're doing, Isles. So did the expansion add like a new world, essentially? You notice that the 4-digit 7-segment displays... That's a 7-segment display. I remember coding for these. It's always quite confusing. Needs a lot of logic gates. Each digit of a 7-segment display is rendered by turning on or off any of 7 segments named A through G. So to render a 1, only segments C and F would be turned on, the rest would be off. To render a 7, only segments A, C, and F would be turned on. Yeah, okay. The problem is that the signals which control the segments have been mixed up on each display. The submarine is still trying to display numbers by producing output on signal wires A through G, but those wires are connected to segments randomly. Oh no. Worse, the wire segment connections are mixed up separately for each 4-digit display. Hello, DJ. All of the digits within the display use the same connection set. So you might know that only signal wires B and G are turned on, but that doesn't mean segments B and G are turned on. The only digit that uses 2 segments is 1. So it must mean segments C and F are meant to be on. Right? With just that information, you still can't tell which wire BG goes to which segments CF. Wait, so... So they're talking about if we're trying to display a 1. But what is it we actually see? We just see the segments, right? We don't see what the wires carry. So if we see... We see 2 segments light up. We know a 1 was pressed. But it's wired, they're wired to the wrong segments. Okay. For each display, you watch the changing signals for a while, make a note of all 10 unique signal patterns you see, and then write down a single 4-digit output value. Four-digit output value. That's more than 4. What? Using the signal patterns, you should be able to work out which pattern corresponds to which digit. For example, here's what you might see in the single entry in your notes. Okay. Let me just look at the inputs so I understand what... Okay. These are entries. Single 4-digit output value. Oh! I see. It's on the right. Okay. So the pipe symbol is separating the, that's the 4-digit output value. Okay, so you look at the signals, you see, you identify all 10 unique signal patterns, doesn't matter the order, so you see 10 different possible lighting up of the segments. And just looking at that, we can see that's the 1, because 1 is the only one with 2 segments lit up. So 1 is corresponding to AB, and like DAB is using the same 2 as 1. So that would mean it's a 7. Because plus 7 is the only one that uses 3 segments anyway. Okay, fine. So I get what that means. So each entry consists of 10 unique signal patterns, pipe delimiter, and finally the 4-digit output value. So what do we want to do with the... What's the point of the 4-digit output value? Within an entry, the same wire segment connections are used. The unique signal patterns correspond to the 10 different ways the submarine tries to render a digit. You should be able to work out which combination of signal wires corresponds to each of the 10 digits. Okay, we can deduce stuff. Then you can decode the 4-digit output value. So we just want to know what the 4-digit output value is in terms of decimal. All the digits in the output value use 5 segments are more difficult to deduce. And now I'll focus on the easy digits. Consider this larger example. Because the digits... Basically, they added the Dark Island artifact, and that one unlocks extra puzzles on the other islands. Okay. So they're giving us... Okay, so we're only focusing on these 4 digits now. So we know a 1 means there's 2. A 4... 1, 2, 3, 4. A 4 has 4. And is it the only one that does? Yeah, it is. Okay. And 7 or 8. Oh, so it... Okay, part 1 is literally just count... Count how many of these have 2, 3, 4, or 7. Okay, fine. We'll just do that then. Okay. Okay, so for now we just want to say left, right equals line dot strip dot split on pipe with 2 spaces. Is that 1 space here? So right equals, let's just split it into the 4 tokens. So okay. So for now we can just in so it's got to be what, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. $375. All right. Part 2. Well, that was, I mean, that was really easy. Just count the number of those token sizes. Through a little deduction, you should now be able to determine the remaining digits. Consider again the first example above. After some careful analysis, the mapping between signal wires and segments only makes sense in the following configuration. So the unique signal patterns would correspond to the following digits. So we're basically solving a Sudoku. Okay, we can do that. So you're told the 10... Okay, so there's 2 layers to this. We have to work out what the digits are. Work out what the Y is. Well... Why do they not give it in alphabetical order? Does the order matter? I don't think it does. So it's equivalent to saying A, B, C, D, E, F, G, isn't it? Should be. So we have to order them. Okay. We don't have to work out what all of them are. We just have to work out what those 4 are. So they might give us examples where it's impossible. Although I think it probably is usually possible to work out what everything is. But you only need to work out what these 4 are. So whenever it's 2, 3, 4, or 7, we know what they are. I guess we want to make some maps. So like 0, 6, 1 is 2. Oh, okay. Let's just create some maps here. So let's make a map which says how many, given a number of segments, which digits this could be. So it'd be like possible digits. So it'll be like 2 maps to 1. It can only be 1 in that case. 3 maps to 7. 4 nope. 4. What was that one? That maps to 4. Um, 2, 3, 4. Let's see, 0 is 6. 2 is 1, 2, 3, 4, 5. So 5. That can be 2, 3, 5, 2, 3, or 5. Six can be... Zero, 6, 9. And then, of course, 7 can only be 8. Okay, so basically we know what these 4 are, and if we get these 2, then there's 3 possible values they could be. Okay. Okay. So generally there will be... So in our list of 10, there will be 6 that we don't know. 4 that we do. 3 of them of size 5, 3 of them of size 6. And that's always going to be the case with no other information. And then when you consider the segments... I mean, I think there's some quick rules we can use to immediately deduce, like, which one is the... Okay, let's have a look at this. So we know what the 1 is, and it has the C and the F. So if we're trying to distinguish between 5, 2, 3, and 5, of those 3, the only one that uses the C and F is 3. So we can immediately identify which one's the 3. It has to contain the same segments that the 1 did. So that tells us which one's 3. And it also tells us which one's 6, because it's the only one without the C and the F. So we've just got a rule. We've got a rule that identifies 3 and 6. Okay, that's a start. So once we've got 6, we would know the other two are 0 and 9. And for that, we just choose the one which has the 4, because 9 contains a 4. So we choose the one that contains the segments of 4, that identifies 9, and then we also get 0. So what's left? We just need to distinguish between 2 and 5. And for that... what's the easiest way to do that? Just... Well, 5 is contained in 9, and 2 isn't. So are we done? That is one process we can do to identify every single digit. Yeah. And then we just have to code that. Not too tricky. Okay. That's actually easier than I thought it would be, because I thought we might have to do something a bit more Sudoku-like. But if there's a process which definitively, like, rules them out, then you kind of have to do something a bit smart. But in this case, I think we do have such a process. We don't even really... yeah, okay, we don't... Okay. So, let's write a method. Given an entry, which is the list of strings, just find a mapping No, we want a decoding. We want... that decoding, which just says this string is this number, and so on. Alright. Also, we should really sort them so that we don't have an issue with order. So let's assume we're given that sorted. Right, so we want... oh, we don't need to even do that. We can use set difference and stuff, set operations to do it. So yeah, we don't need to sort them. So decoding is that. Alright. So we look through the entry. Alright, let's just fill in the 1, 4, 7, 8. Okay, so for digit in entry, if length digit equals 2, then decoding is 1. If it's 3, then it's 7. Otherwise, if it's 4, 7, it's 8. Okay, so we do a first pass so that we know where the 1, the 7, the 4, and the 8 are. And then on the next pass, we should be able to work out everything else, given that we already know those. And we want to make a note of the 4, so let's say 4, just create a variable called 4 equals digit, and create a variable called 1, because those two are special that we'll be using to deduce other things. Alright. Now that we know those, we'll make a second pass through all the digits. For digit in entry, if it's 5, we know we're either 2, 3, or 5. Okay. So what was the first step? First we check if it contains 1. If it contains 1, that means it's a 3. So if set, so we turn 1 into a set, and we do contains 1. Is that right? No, you don't do that. What do you do? I gotta look this up again. Set.is subset. So if set1 dot is subset of set digit, then decoding digit equals 3. Okay. elif, and then how did we distinguish the 2 and the 5? Oh, we used the 9. Well, instead we could... that means we have to do a third pass. Instead, we could just work it out now by saying, okay, so... we use the 4. We just find the... how much in common 4 has with 5, so it should be 3. And with 2, it's just 1. Oh, okay, okay. So we take the intersection So we say elif set for intersect. How do you intersect sets? It's that, right? I've got to look this up. You can just do dot intersect as well, but what's the quick method? Yeah, it's the ampersand. So step 4 and set digit length is 1. Then it can only be a 2. Because it's just that middle bar. Okay, so that identifies those. And then we're on to the 6. Alright, now for this one, we check if it contains 1 again. That would... no. Yeah, that will identify the 6. So... if 1 is not a subset of it, then that means it's a 6. So that in that case we've just got 0 and 9, and 9 contains the 4. So elif set 4 dot is subset of that, then it's a 9. Else it's a 0, and that's everything. 2 passes. Can be done in 1 pass. Well, not really, because you need to know where the 4 and the 1 are, so you need 2 passes, really. Okay. Now what do we do with that? So we want to first just fully decode the left-hand side, even if we don't need all the digits. And then... alright, so... okay, left... so... left equals left dot split. And we never need to sort them because we're using set operations anyway, so it doesn't matter if they give us AD and DA or whatever. It looks like... yeah, they do look. So that there's AD here, but then there's DA, DA. So the order, they do mix up the order here. Left equals left dot split. Now we want decoder equals solve left. This has to be defined beforehand. Token and write Result 1 plus equal that. So what is the ultimate thing they want us to compute here? Decode the 4-digit output values. What do you get if you add up all of the output values? So first we have to create a string to contain the output. So let's do part 1, and we output plus equal decoding. No, wait. The order does matter here. Unless they always kept the order between the left and the right side, but I don't see any reason why they... We shouldn't assume it. A, D, B, G, C, F. A, D, B, G, C, F. Yeah, they do actually mix up the order. Fine. That means when we do the decoding, we have to so we take the sorted X. So now the decoding should be sorted. Hopefully I've done that right. Output plus decoding. And then we'll have to do string sorted token. Then result to plus equal int the output. Just comment that out for now. I should have... Okay, fine. Oh, that's not how that works. How do you sort a string? Oh, you have to... Sorted X would give a list, and then you've got to do... Okay. Like that. Only concatenates string, not into string. That's a string. These need to be strings. Not. Or do we prefer them as digits? I don't know. It's a. They have numerical meanings. We'll return it as a digit, but here we'll have to just cast it to a string. Alright. Hopefully this works, because it's easy to get a few things wrong here. Nope, it's too high. I think the fact that this completes, so I think the idea of the process is correct. Just a mistake somewhere, I guess. So oh no, this is wrong. Oh no, that's right. That's right. 9 contains 4. Look at the diagram again. 9 contains 4, 0 doesn't. Yeah, that's right. Did we still get... Wait, so part 1 was 375. Yeah, that's the same. Now, the fact that it actually gets an answer at all really indicates that the error is just in this logic here, because what else could have gone wrong? Well, hang on. I could have... This bit could be some... Sort of left us... So we are sorting them. Sorted token, yeah. Let me just print the outputs. That's what the outputs look like. They're all 4 digits. Uh-oh. Wait, no, that's fine. Wait, okay, so we've got those two the same. Does that happen? Yeah, it does. Yeah, that's right. Looks plausible. Alright, we'll try the test example then. Six one two two nine. Why did you do this? Put them on separate lines like this, damn it. can't we get it as a... putting the test case in a different format to the... Alright. 61259. And we should be getting 61229. So we're very slightly off. Surprising. Okay. Let's go through the numbers. 8394, correct. 9781, correct. 1197, correct. 9361, correct. 4873, correct. 8418, correct. 4548, correct. 16, uh-oh. So we should have 1625. We got 1655. But the other two, 8717, correct. 4315, correct. So we got 1655. Should have been 1625. How did I distinguish between 2 and 5? I said that. Oh, I see the problem. What was my logic? So to distinguish between 2 and 5, I said that it has an intersection of 1 with 4. But if you actually look at the diagram, so if you try to intersect the number 4 with 2, it should be 2. And if you try to intersect 4 with 5, it should be 1, 2, 3. So it's 2 and 3. So if it's 2, then the answer is 2. So if that's 2, then it's 2, otherwise it's 5. 61229. Yep, okay. Hopefully that's right now. Otherwise we're in big trouble. All right. Stay 8. That was an interesting problem. They could have made it a lot harder if they made a like my process for solving it was a fixed number of steps. Like you can get every digit as long as you just follow this one process. But you could make it closer to a proper Sudoku where everything you look at can rule out certain options, and then there's no knowing how many cycles you have to go through, crossing out possibilities until you got unique ones, and then yeah, it could potentially be a very difficult problem. And I mean, yeah, the fact that it's a 7-segment display imposes a lot of restrictions, so I guess it's actually kind of hard to make it a bit more like a Sudoku, because you're already completely identifying 1, 4, 7, and 8 or whatever. There's no getting around that. And then there's not much left. Yeah. Okay. I can go for one more. And we'll have some plants with zombies later. Plants versus zombies, not plants with zombies. Day 9. Day 9, smoke basin. These caves seem to be lava tubes. What is a lava tube? The cave formed by lava. That's cool. Parts are even still volcanically active. Small hydrothermal vents release smoke into the caves that slowly settles like rain. If you can model how the smoke flows through the caves... Ooh, we've got a flow problem. You might be able to avoid it and be that much safer. The submarine generates a height map of the floor of the nearby caves for you. Smoke flows to the lowest point of the area it's in. For example, consider the following height map. Each number corresponds to the height of a particular location, where 9 is the highest and 0 is the lowest a location can be. Your first goal is to find the low points, the locations that are lower than any of its adjacent locations. Okay, so it's like a trough. Most locations have 4 adjacent locations. Locations on the edge or corner of the map are 3 or 2, respectively. Okay, so we need a neighbor function. And then a trough is basically something which is strictly lower than all of its neighbors. Strictly lower, not lower or equal to. Yeah. So therefore... the risk level of a low point is 1 plus its height. Okay. That's alright to start with. So to start with, I guess we just want to store the grid. Or should we store them as ints? Because we actually care about their values. Right, just take a quick peek at this grid. Yeah, looks about right. Okay. And then we want... okay, so we can say height equals length of grid, width equals length grid 0. So let's define get neighbors. So given an I and j, we want to return all the neighbors. So it's going to be -1, 0, 1, 0, 0, -1, 0, 1. If so, it's going to be 0 is less than or equal to neighbor I is less than height, and 0 is less than or equal to neighbor j is less than width. And this is a valid neighbor, so yield neighbor I, neighbor j. Okay, that's get neighbors. So the processes go for I in range height, for j in range width. If all, so we want to check if the grid say h is the value that's at grid ij. So if all the neighbor values are strictly less than h for neighbor I, neighbor j in get neighbors of I and j. So even if it's at the corner, there'll only be 2 values, but if all of them are less than all valid neighbors, oh no, it's the other way around. All valid neighbors are greater than h, then that means ij is a trough. What do we do with that? We add 1 to it. We add up all the risk levels, and the risk level is 1 plus the height. So result 1 equals 0. Result 1 plus equals, so it'll be h plus 1. Print result 1. 535. Correct. Next, you need to find the largest basins so you know what areas are most important to avoid. Basin is all locations that eventually flow downward to a single low point. Therefore, every low point has a basin, although some basins are very small. Locations of height 9 do not count as being in any basin, and all other locations will always be part of exactly one basin. The size of a basin is the number of locations within the basin, including the low point. So this is basically flood fill. We take the low points. From each low point, we do flood fill to find everything that would flow into that basin. And they've said exactly that there can be exactly one. So you can't have it go up to 5 and then go down to some other trough. It seems that it always only goes up to 9 at most. 9 is like the ridge that separates all the basins. Wait, doesn't that basically mean that so basically the 9s form a border around all the basins, that's it. We still need to use flood fill. Even with that knowledge, we still need to use flood fill because we don't know. Just by looking at the border, we can't identify easily how many regions there are. We need to work out how they connect up and everything. All right. Find the 3 largest basins and multiply their sizes together. Okay. So we just want a list. We want a list of all the basins, and then we can work that out. So okay, this is flood fill, just straightforward. So when we found a trough, that basically identifies a basin. But we want to find how many elements are in that basin. So at this point, INJ is a trough. Alright, let's do... So we're going to have to write a... just like a basic DFS. All right, so start from this J. We put this on the Q. We don't care about distances. Put that, but we have a visited set as well. While Q, so we just take stuff off the Q. Q pop. And then we do for neighbor I, neighbor J in. Also visited will be a set. Neighbor I, neighbor J in get neighbors. So first we need to make sure it's not 9. So if grid I J is 9, skip that one, that's not part of a basin. Otherwise, if this was visited before then it was already on the queue at some point. So continue. Otherwise, we pop it on the queue. Should really just say neighbor equals that. Put it on the queue. Mark it as visited. Then what? Once we've done all of that, it's just the size of visited. That's all we care about. This is basically telling us get basin size for a given trough. It works on any element in the basin. All right. Basin sizes is just a list. All right, now. So we found a trough. We just want to do basin sizes dot append get basin size neighbor I neighbor j. No, I for ij. And then basin sizes dot sort. Reversed. So we start with the biggest. And then we want to print basin sizes 0 times basin sizes 1 times basin sizes 2. Is that what they wanted? Multiply the 3 biggest. Okay. Correct. Okay. That was a nice flood fill warm-up. Nothing particularly difficult, just write the most basic DFS. You don't need to measure distances. You don't need to keep track of the actual set of elements, or at the end of the day, you just want to return the size of the set. So you just use a basic set to keep track of what you visited, and yeah, that's the most fundamental. The only complexity is that you had to do it more than once. But that's about it. And you had to recognize that the 9s form the border, which was pretty much spelled out in the description, but that was the first like search problem of this year. Surprising, because last year's actual live competition, we had a lot of BFS DFS, a lot of those. It was full of flood fill problems. Some of them were kind of repeats of past ones, just with different blurb, but yeah, we had a lot of searching, which I mean is fine. It's a very important algorithm, and it's one of the most practical as well for doing real things. I mean, this is exactly the kind of algorithm you'd use to find real basins and real contour maps of real life locations. I mean, it all comes down to this. You just have more granularity of the points, probably, but... So we've done day 9. I think we'll stop there. Yep, that's about a third of the way through. Looks like 19 might be a tricky one. Got a bunch of people who've done this. Miss Smabube K, I know, is... I think he's done every year now. Captain Coda. I haven't heard much from Captain Coda lately. I don't think he's been streaming much. He might be doing another game jam at some point, like he did last year. Alright, well, I don't really want to do 10 right now, so... Oh, Smap UK, speak of the devil. This is the only year I have 50 stars on, though. Just got here. Oh, welcome in. Yeah, I've just... This is the last year I need to... Oh, it's the only year you have 50 stars on. Do you think it's an easy year, then? So far, it seems quite easy. Yeah, this is the last one on my list. Until I get the much coveted 500 star. Oh, I was gonna look at Captain Coda's leaderboard as well. I see that Captain Coda has done part 1 of day 25. I don't know why. Did he accidentally pick the wrong year at some point when he was doing it? Or maybe he just for some reason wanted to do that specific problem. The only year I persevered through the types of problem I hate. Did you do this one live? I think the first one I did live was like 2019, and then I left a gap, and then I came back in 2022, I think. So yeah, I'm going back and finishing them off. Yeah, 2019. Was this the first one I did? Yeah, I think I did this one live. No, I didn't do this one live. I did this one just last year. I was archived. 2020 was the one I did live. The first one I did. All right. Well, I don't know if anyone really streams Advent Code these days because it's mid-year, so it's unlikely. Yeah. All right, that's it for today. Might do a bit tomorrow, probably a bit earlier. That might mean it's like the middle of the night for a lot of people in America or even Europe, but it's more of an afternoon thing for me to do. All right, thanks for watching. See you next time.